Have you ever paused to watch a water strider effortlessly skate across the surface of a pond, its delicate legs barely breaking the water's calm? It almost looks like a magic trick, but there's real science at work here. Or maybe you've noticed how a drop of water stubbornly clings to the edge of a faucet, refusing to fall. These everyday wonders aren't magic, they're the result of fascinating physics. Surface tension and capillarity are the invisible forces that shape how liquids behave. They're not just scientific curiosities, they're essential concepts for engineers and scientists alike. Ever wondered why a paper towel can soak up a spill so quickly and efficiently? Or how a fountain pen manages to deliver a steady, precise flow of ink onto paper, line after line? The answer lies in these same unseen forces, surface tension and capillarity at work behind the scenes. These forces aren't just interesting, they form the foundation of countless engineering solutions, from the smallest lab equipment to massive industrial machines. Today, we'll uncover what these forces are, explore how they work in the real world, and discover why they matter so much in technology and nature. From the thin film of oil in engines to the precise flow of material in 3D printers, these tiny interactions have massive impacts on performance and innovation. So, let's dive into the invisible architecture that allows liquids to climb walls, power machines, and keep our world running smoothly. Our first stop, the stretchy, invisible skin of water, where the magic of surface tension begins. Surface tension is like an invisible, elastic skin stretched tightly across a liquid's surface, holding everything together in a delicate balance. Imagine a crowd of people at a concert. Those on the edge are pulled inward by the group, making the whole crowd tighter and more compact. Water molecules at the surface behave in a similar way, clinging to each other more strongly than to the air above. This invisible film is what allows insects like water striders to walk on water, and why raindrops form into perfect, shimmering spheres as they fall. Surface tension, often symbolized by the Greek letter gamma, is defined as the force per unit length along the surface of a liquid, measured in newtons per meter. You can even try this at home. Gently place a paperclip on water and watch as it floats. It's not magic. It's the molecular skin of water holding it up against gravity. This effect is driven by cohesion, the attraction between like molecules, which pulls them together and creates that surface film. In water, hydrogen bonds make this surface tension especially strong, giving water its unique properties. Mercury, for example, has an even higher surface tension, causing it to form tight, round beads, while water's lower tension lets it spread and stick to surfaces. For engineers and scientists, controlling surface tension is crucial for determining how liquids spread, bead up, or adhere to different materials and surfaces. Whether it's lubricating moving parts, cooling industrial systems, or fueling engines, understanding this invisible force is essential for countless technologies. Surface tension is a subtle but powerful force, one that we can harness and manipulate in every design, from the tiniest droplet to the largest machines. Now, let's meet capillarity, a fascinating phenomenon where water seems to defy gravity and climb upwards, all on its own. This is what happens when liquids climb against gravity, moving upward instead of simply flowing down. Dip a thin tube in water, and you'll see the liquid mysteriously rise inside, higher than the water outside the tube. That's because adhesion, the attraction between water molecules and glass, overpowers cohesion, which is the pull between water molecules themselves. Surface tension then pulls the rest of the water up, creating a delicate balance until gravity finally stops the climb at a certain height. The narrower the tube, the higher the climb. Thin tubes let water rise surprisingly far, while wider tubes barely lift it at all. Scientists can even predict this rise with a formula that combines surface tension, contact angle, density, gravity, and the radius of the tube. But capillary action isn't just a laboratory curiosity. It's everywhere in our daily lives and in nature. It's how paper towels soak up spills, drawing liquid deep into their fibers almost instantly. Plants rely on capillarity to draw water from their roots all the way to their leaves, fueling life itself. In engineering, capillarity moves fluids into tiny spaces. No pumps or external force needed, just the power of molecular attraction. It's used to wick oil into engine parts, ensuring smooth movement and reducing wear. Capillarity also helps distribute fluids evenly in porous materials, from building materials to advanced electronics. This passive, reliable force is a gift for precise fluid control, making it essential in science and industry. By mastering capillarity, engineers can move liquids exactly where they're needed, with incredible accuracy and efficiency. All of this is powered by the invisible dance of molecules, tiny forces working together to move water uphill, one drop at a time. In machines, lubrication is everything. Oil must reach microscopic gaps to prevent wear. Capillarity pulls oil into tight spaces, while surface tension ensures it spreads evenly, no dry spots. Engineers tweak oil's properties to get the perfect balance, so it sticks where it's needed. For cooling, heat pipes use capillary action to move liquid back to hot spots, all without pumps. The wick inside acts like a sponge, cycling coolant efficiently and passively. This interplay of forces keeps engines running and electronics cool, even in space. It's elegant engineering, powered by nature's smallest forces. Filters rely on capillarity to move fluids through tiny pores, separating what we want from what we don't. Hydrophobic filters block water but let fuel pass, using differences in surface tension. In fuel injection, surface tension breaks fuel into a fine mist for efficient combustion. The nozzle's design and fuel's properties control droplet size and spray. Lower surface tension means better atomization, cleaner burning, and higher efficiency. Engineers fine-tune these forces for performance and emissions. Microscopic control leads to massive real-world impact. Master the small, and you master the machine. In 3D printing, capillary action pulls binder into powder, fusing layers with precision. Surface tension controls how far the binder spreads, too much or too little, and the part fails. Engineers adjust binder and powder properties for perfect results, layer by layer. In microfluidics, tiny channels use capillarity to move fluids, no pumps required. By designing channel shapes and surfaces, engineers create passive valves and mixers. This tech powers rapid medical tests and chemical analysis on a chip. At this scale, surface tension and capillarity rule. The future of engineering is built on mastering these forces. From bugs on ponds to satellites in space, surface tension and capillarity shape our world. They keep engines lubricated, electronics cool, and fuel burning clean. Small changes in these forces can mean the difference between success and failure. Engineering is about seeing the big impact of tiny details. Next time you see water bead or a spill get soaked up, remember, invisible forces are at work. Mastering them is the key to innovation. Stay curious. The world's most powerful forces are often the smallest.